Hello, everyone, and welcome back to the Swivel Embedding series. In the previous video, we introduced the motivation behind Swivel and discussed its core idea. We reviewed both Word2Vec and GloVe and saw that 0 entries in a co-occurrence matrix do not always mean the same thing. We also learned that Swivel's key idea is to explicitly model these unobserved co-occurrences instead of simply ignoring them. In this video, we'll take a closer look at the two fundamental concepts behind Swivel: Pointwise Mutual Information, or PMI, and low-rank matrix factorization. So why does Swivel use PMI instead of simply using raw co-occurrence counts? The reason is that PMI provides a much better measure of the semantic association between two words than raw co-occurrence counts. Before we introduce PMI, let's first look at the limitations of raw co-occurrence counts. One major problem is that they are heavily influenced by word frequency. For example, let's say we have the following word pairs and their co-occurrence counts. If we look only at the raw counts, the pair the and of appears to have the strongest relationship. However, these are simply very common stop words that appear almost everywhere. On the other hand, the pair deep and learning has a much smaller raw count, but the two words are much more strongly related in meaning. In other words, raw co-occurrence counts alone do not necessarily reveal meaningful semantic relationships. This is exactly the problem that Pointwise Mutual Information, or PMI, was designed to solve. Unlike raw co-occurrence counts, PMI does not simply ask, how many times did these two words appear together? Instead, it asks a more meaningful question. Given how frequently each word appears individually, how much more often do they co-occur than we would expect by chance? The formal definition of PMI is shown here. The PMI between target word I and context word J is defined as the logarithm of the joint probability of the two words divided by the product of their individual probabilities. Here, Pij is the probability that word I and word J occur together. And Pi and Pj are the probabilities that each word appears independently. Let's assume that the two words are completely independent. In that case, the probability of seeing them together should simply be the product of their individual probabilities. That product represents the expected probability of co-occurrence under independence. If the actual probability of the two words occurring together is much larger than this expected value, the fraction inside the logarithm becomes greater than 1 and the PMI becomes positive. A positive PMI tells us that the two words co-occur more often than we would expect by chance, suggesting a meaningful semantic relationship. On the other hand, if the observed probability is close to the expected probability, the ratio becomes close to 1 and the PMI is close to 0. In that case, the two words behave almost as if they were independent. In this example, the words deep and learning are likely to be semantically related because they co-occur much more often than would be expected by chance. As a result, they are likely to have a high positive PMI. In contrast, the words the and of have a very high raw co-occurrence count, but they would be expected to have a much lower PMI than the raw count alone would suggest. This is the key advantage of PMI. A co-occurrence matrix stores how often words appear together. A PMI matrix, on the other hand, captures how strongly words are associated with one another after accounting for word frequency. For this reason, Word2Vec, GloVe, and Swivel are all closely related to PMI, even though they approach the problem in different ways. Swivel also learns its embeddings, so that the dot product between the target embedding WI and the context embedding CJ approximates the corresponding PMI value. However, there is still one important problem. The probabilities in the PMI equation are the true probabilities we would obtain from an infinitely large corpus, but in practice we never know their exact values. We only have access to a finite corpus. That means we need to estimate these probabilities using the co-occurrence counts that we actually observe. This leads us to empirical PMI, which replaces the theoretical probabilities with observed counts. Let's consider the following co-occurrence matrix. The rows correspond to target words denoted by W, and the columns correspond to context words denoted by C. Each entry in the matrix Xij represents the number of times target word Wi and context word Cj co-occur in the corpus. To convert these counts into probabilities, we first compute a few useful totals. The value xi star is the sum of all the entries in row I. In other words, it represents the total number of co-occurrences involving target word Wi. Similarly, x star j is the sum of all the entries in column j, representing the total number of co-occurrences involving context word cj. Finally, the size of D is the sum of every entry in the matrix. It represents the total number of observed co-occurrences in the corpus. Using these quantities, we can rewrite the probabilities in the PMI equation. The joint probability Pij can be written as Xij divided by the size of D. Similarly, Pi can be written as Xi star divided by the size of D. And Pj can be written as x star j divided by the size of D. Substituting these expressions into the original PMI definition gives us a new equation. This is called empirical PMI because it is computed directly from the observed co-occurrence counts rather than from the unknown true probabilities. If we expand the logarithm, we obtain the following expression. Here, these two negative logarithm terms act as correction factors that reduce the impact of word frequency. Words that appear very frequently receive a larger penalty, preventing them from dominating the PMI values. For example, the word "the" has an extremely large xi star, so the term minus log xi star becomes more negative. As a result, the PMI value is reduced, correcting the misleading impression created by the raw co-occurrence count. This is exactly why PMI works so well. Now that we understand PMI, let's revisit GloVe from a slightly different perspective. In the previous slide, we saw that PMI can be written in this form. If we simply rearrange the equation, we obtain the following expression for log xij. Here, the term log the size of D is simply a constant, since it depends only on the corpus and not on individual word pairs. This equation reveals an important connection between GloVe and PMI. Swivel is trained so that the dot product between two embedding vectors approximates the corresponding PMI value. GloVe, on the other hand, appears to learn the logarithm of the co-occurrence count. At first glance, these objectives look quite different, but they're actually much more closely related than they seem. As we discussed in the GloVe series, the GloVe objective includes two bias terms, one for the target word and one for the context word. During training, these bias terms naturally absorb the frequency-dependent terms log xi star and log x star j. The constant term log, the size of D, is also absorbed into the bias. As a result, although GloVe is formulated in terms of log xij, the learned embeddings end up capturing something that is very close to PMI. It tells us that GloVe is not simply learning co-occurrence counts. Instead, it is implicitly learning the PMI structure hidden behind those counts. Swivel takes this idea one step further. Rather than relying on the bias terms to recover PMI indirectly, Swivel makes PMI itself the direct learning target. In other words, the model is trained so that the dot product between the target and context embeddings directly approximates the PMI matrix. This gives us an important insight. Although SGNS, GloVe, and Swivel use different objective functions, they all share the same underlying goal: to learn vector representations that capture the PMI signal hidden within the co-occurrence statistics. The main differences lie in how they approximate that signal and which parts of the co-occurrence matrix they emphasize during training. Now that we've seen why PMI is the target, the next question is, how can we represent an enormous PMI matrix using compact word embeddings? The answer is low-rank matrix factorization. Our goal is illustrated in the figure shown here. On the left is the PMI matrix, whose size is V by V, where V is the vocabulary size. On the right are two much smaller matrices, the target word matrix and the context word matrix. The target word matrix has size V by M, and the context word matrix has size M by V. Here, M is the embedding dimension. In practice, M is usually a few hundred, while the vocabulary size V may be tens or even hundreds of thousands. In other words, M is much smaller than V. As shown in this figure, low-rank matrix factorization approximates one large matrix using the product of two much smaller matrices. Instead of storing every value in the original PMI matrix, we represent each word with a low-dimensional embedding vector. The dot product of these vectors then approximates the corresponding PMI value. Rather than memorizing a massive matrix, we compress its essential structure into a compact vector representation. This idea is not unique to Swivel. In fact, GloVe and even older methods such as latent semantic analysis, or LSA, are built on the same fundamental principle. From this perspective, Word2Vec, GloVe, and Swivel all share the same underlying goal. They all seek to represent the statistical relationships hidden in co-occurrence data using low-dimensional vectors. However, there is still one important challenge. If two words never appear together in the corpus, their co-occurrence count xij becomes 0. Mathematically, log xij goes to negative infinity when xij is 0, creating a serious problem. If an unobserved word pair produces a PMI value of negative infinity, how should the model learn from it? Should we simply ignore these entries? Or should we treat them differently, recognizing that some zero counts may simply result from limited data rather than a true lack of semantic association? As we discussed in the previous video, not all zero-count pairs carry the same meaning. Some word pairs never appear together because they are genuinely unrelated. Others may simply be missing because the corpus is too small to capture every meaningful relationship. This is exactly the challenge that Swivel was designed to address. Rather than ignoring these unobserved co-occurrences, Swivel models them explicitly in a statistically principled way. We'll see exactly how it does this in the next video. In this video, we explored Pointwise Mutual Information, or PMI, and low-rank matrix factorization. In the next video, we'll see how Swivel converts these ideas into a practical objective function, how it uses different loss terms for observed and unobserved word pairs, and how it scales training efficiently by dividing the PMI matrix into small blocks for parallel computation. Thank you for watching, and I'll see you in the next video.